קהל נכבד, אנחנו התחלנו, אנחנו מבקשים מכולם לשבת ובבקשה לשמור על שקט באולם. תודה רבה.
Und dann schalten Sie mich erst, kann ich das aus und dann mute, das ist gut.
Okay. Good morning, ladies and gentlemen, and welcome to the ATV4 in-flight call event. My name is Nigel Savage. I'm the Education Officer for the Human Spaceflight and Operations Directorate at the European Space Agency, also known as ESA. I'm currently talking to you here from ESTEC in Noordwijk, the Netherlands, the technical center of ESA. Joining us today by video conference are three other remote sites: Politecnico di Milano in Italy, the Technical University of München via the Leibniz Supercomputer Center in Germany, and the Hebrew University of Jerusalem in Israel. The purpose of today's events is to celebrate successful completion of the mission of the fourth automated transfer vehicle, or ATV, named after Albert Einstein. This particular ATV mission is due to undock from the International Space Station on the 28th of this month, just before 10 a.m. Central European Time. ATV, as you will hear later today, could be regarded as one of the most sophisticated space vehicles built to date, and its automated approach to the ISS is unprecedented, making it much more than a cargo vehicle, but, as it turns out, also a robot. You will, in the afternoon session, learn more about the vehicle, the missions, past and present, and the dependency of the ISS on the ATV program for cargo and altitude correction. So in order to celebrate the inevitable synergy of robots and human presence in space, the European Space Agency, with its partners that I mentioned earlier, have organized a two-part event for students first and foremost, but also dignitaries and press in the afternoon. The morning session will be exclusively dedicated to the several hundred students participating at each site and will encompass 3 lectures from distinguished academics in the field of robotic science and mission operations. The afternoon session will encompass a local program of lectures and presentations of ESA's ATV4 Mission Director Alberto Novelli, live from the Hebrew University in Jerusalem. After these presentations, we will then connect to the International Space Station, where students will be able to talk live to ESA astronaut Luca Parmitano. Back to the morning session now. Each lecture will be immediately followed by a 10-minute question and answer session, which I will moderate, and therefore giving students at each site the chance to ask the presenter questions. So please save your questions for the end of the lecture. I would also ask the auditorium staff of the sites asking the questions to please hand microphones to the students so that we can hear the questions clearly. Our first lecture today will be broadcast from Politecnico di Milano, where Professor Amalia Ercoli Finzi has headed the Department of Aerospace Engineering for over 25 years. Professor Finzi is well versed in space research areas covering diverse topics such as space mission design, attitude control, rendezvous and docking maneuvers, to name a few. Currently active in ESA's mission Rosetta, she is the principal investigator of the PD2 payload on Friday, which will drill into the comet. Also active in the Google SpaceX Prize competition as team leader of Team Italia, one wonders why the robot is called Amalia. In her lecture, Professor Amalia Ercoli Finzi will discuss some of the solutions developed for robotic missions with particular focus on power, locomotion, guidance, navigation, control, and thermal production. Dear Professor Finzi, I shall give you now presentation rights. Please share your application via WebEx, and you may begin when you're ready. Thank you. The floor is yours.
May I start? It is a pleasure to be here and to welcome all of you for this event that in my long life is particularly important because it is the demonstration, the proof, the demonstration that the world is so small that we can stay together even if we are so apart. Our lecture will be divided in, my lecture will be divided in 3 parts because I will present the 3 points of view. The first one is mine, and it is the one of the mission design, space mission design. What is a robot for a mission designer? The second one will be devoted to, taken by Professor Magnani, that will talk about the robot design. And the last one is the point of view of the industry that will that had to design to build the robot. From my point of view, the question.
Dear Professor Finzi, can you hear me? I'm sorry to interrupt your lecture. We seem to be having some audio issues, and I was wondering whether your technical staff can maybe increase the audio.
What's the problem? Vediamo un po'. Now it's better?
Please keep talking.
Nigel, now it's better?
Now is better. Thank you very much. Apologies for interruption.
I cannot. I wanted to, what is a robot for me? For me, I am a mission designer. A robot is myself, is another myself that is on a distant planet and does what I ask him to do. I wanted to show you the difference between the very first robot we sent to space and the very last robot we sent to space, just so you can appreciate the difference between the two. I wanted to talk about Mars because it was not the very first robot space robot was not devoted to Mars, was devoted to Venus. But I prefer Mars because Mars is a very interesting planet, and we are going to Mars just to find water. That's our goal. We can see that on the North Pole of Mars there is water. This is a picture taken by an European satellite that is Mars Express that pictured this ice in Vastitas Borealis, that is a lowland in Mars in the North Pole. Exploration of Mars started in 1960. But it was not a good idea, a success. Mars is a terrible planet and it was very difficult to find. But I wanted you to appreciate that it was on 60, that means 3 years after the launch of Sputnik. It means we started immediately. The first robot we succeeded to launch to Mars was done in 1971 when Mars 3 on 2 December released a robot to Mars surface. This mission was composed by an orbiter and a lander. The orbiter was Mars 3 probe that was launched by a proton case with a four stage, that means a four-stage launcher, then to put it in a wrong orbit. It happens. The original orbit would be for 25 hours orbit, elliptic 25 hours. Instead it was a high elliptic orbit of 13 days. But it happened. In any case, it happens anyway. In any case, when we arrived, I want you to appreciate of this design that the large antenna, our problem is to communicate with the Earth. If you send something, you can't know what it happened. It is like if you had done nothing. But there are two particular things. Can you see the two small antennas all fixed to the solar panel? They were particularly devoted to communication with the lander. And it was a strange solution that Mastri did a lot of beautiful things. He had to study topography of the soil composition, property of the atmosphere, solar radiation, but in particular it was a relay to communicate with the lander. The lander was sent on the surface on 2 of December, just to Christmas. And it was hidden in a conical braking field when was on board some micro engines and gun power engines and the parachute system, a retro rocket, just to guarantee that the lander could arrive on the soil for a soft landing, because some days before we tried to do, our community tried to do a landing on Mars, but it was a crash landing, so it didn't interest us. When you see that the capsule, the lander, is a capsule not very big, that means 1 meter of diameter, 1 meter is like that. It's about 350 kilos. That is not a poor mass for a lander, but in any case it was a beginning. With 4 triangular petals that opens just to maintain right the spacecraft and to expose the instrumentation to the environment. There are 2 television cameras and 1 mass spectrometer just to analyze the components of the soil. There were sensors for temperature, pressure and wind measure, and there was also, that I told you at the beginning, there was a scoop to find the sign of life, organic components that define us. 4 areas just to communicate with the orbiter, and it was sterilized. That is very important because we don't want to create problem to the environment of Mars. There were some batteries that had been recharged before the release of the. And now we arrived. Yes, we arrived. We arrived on the soil, on Mars. We started to transmit, but after 14 seconds, the communication stopped. It happened because there was a strong, a terrible dust storm, and it was recorded by the other orbiters that were orbiting around Mars. A dust storm, and they create a kind of electrical field around the lander, and the battery stops. In any case, we take a picture, one picture, one picture, but we can see nothing. Also because the camera was a special camera, what you use now with mobiles, that is a cycloramic camera. That means that you are not sure that this is the right orientation. Probably the right orientation was the opposite, or put on. That means that we can see nothing. We are sure that we went there. But this is a very short movie, very short. I present to you, and it is original. I don't know how many people know it. It is in Russian, of course. This is the capsule, and you can see the dimension of capsule with respect to men. Aerobraking, and there is someone that is working with a crew. This is put inside a room for experiments, for testing, and we have seen some foam we put just to absorb shocks in case when you land. This is the landing, and this is a simulation of landing with the music was there. But ecco, voilà, this is a test of landing. We see the 4 petals that open. It's not very nice. This is an apparatus for chemical experiments. The other one, now we see an aerial that is devoted to the study of winds. Justin? No. And this is a surprise. The surprise is very small rover, 20 centimeters, and you see, in such a funny way, he's walking on Mars. It's not on Mars. This is very bad. So, the rover was called Prop M. Prop means a device that can work on Mars. I don't know why. And we don't know what it did because it didn't have time enough to do it. But are you sure we went there? Because there is a lot of people that say, no, Russia didn't go there. Yes, we went there. This is a parachute that now has been found on Mars with the analysis of a picture taken by MRO that has a very high definition. I have to run because this is a parachute. The very last we send to robot we send on Mars is Curiosity. Curiosity is completely different because Curiosity has 2 important things. The precise landing and the land a very large scientific science laboratory for on Mars. You can see the constitution, the organization of the lander that is so big, this is the experiment, but in particular, that's important for my students that are aerospace students. We tried, and we had the success to transform this spacecraft in an aircraft. When we arrived in the atmosphere of Mars, there was a system to create a trim angle, and this trim angle was generated a lift angle, so we can guide the spacecraft where we want, exactly where we went. So we went there. This is a very short picture of what happened. We arrived on Mars, and the other thing is how to land on Mars. We deployed the parachute, and we released the so-called sky train that are four nylon tethers that load the Curiosity up to 7 meters above the descent stage, and to let it stay easily on Mars. Now we have about 1 ton, that is gigantic. You mean that it is tall 3 meters. I am 1.5 meters. That means it is exactly the double of me. It is terrible. It can do a lot of things, can do a lot of things, and it is not propelled, alimented by RTG, because it is a political choice of the United States to use nuclear energy, and instead Europe doesn't decide to do that. In any case, are you sure that we went there? Come with me to Mars. We are on Mars. This is a self-portrait done by Curiosity itself with he has 17 cameras, and one of these is on the top of the robotic arm, and taking the 55 pictures. This is not beautiful. It looks like a Martian, no? It looks like a Martian. But in any case, we are there. We are doing a lot of beautiful things, and from my point of view, that's enough. He is doing well. But how to design it, Professor Magnani will teach you how.
I don't know. It's okay. Good morning. I'll give you just a few highlights about what could be called the brain of a rover. In more technical terms, the rover control system. First of all, a short look inside the rovers. Rovers are complex and powerful robots. In fact, as robots, they are able to sense the world around them, to reason about the information they get from the sensor, and keeping into account the goals that they have to pursue. They are able to perform on the environment, to work on the environment, to move and to grasp and move manipulator objects. But rovers are also mechatronic systems. Mechatronic systems are those systems that use combination of mechanical and electronics parts in an integrated way to perform their tasks. Here is an example of what a mechatronic system is. The picture on the top right is that of DEX-ARM, a manipulator arm developed recently by Cerex ES on behalf of ESA. And the other picture concerns a joint of DEX-ARM. DEX-ARM has 7 joints connecting 8 links. Joint permits the relative rotation of two links, between 2 links, and the other pictures show the parts of the joint. The joint consists of an electric motor, a gearbox, sensor, 3 sensors, 2 position sensor and a torque sensor, power electronics, and control and communication electronics. This is an example, but all other sensors, complex sensors like vision systems, cameras, laser scanner, and all we can say all rover subsystems and instruments have their own control electronics and their own control system. I have no reaction from.
Control system is not working.
So, yeah. Anyway, okay, thank you. Okay. Yeah, but I use them. Okay. The way the rover is operated strongly depends on the communication channel between Earth and Mars, for instance. Such channel is very low bandwidth and affected by a very high latency. For instance, the time the light takes to go from Earth to Mars is in the range between 4 and 21 minutes, depending on the relative position of the two planets. And also the channel is available only a few times a day. That means that it's impossible to teleoperate the rover. The rover must be able to execute autonomously operation plans sent to it every day by the engineering and scientific teams. So it must be autonomous. The most challenging autonomous capability is the one that allows it to navigate fast and safe, relatively fast and safe, to operator-defined waypoints over surfaces which are sloping, maybe sloping. There are unexpected obstacles, there are hazards, and so this requires very demanding computing capability. What permits such a high level of autonomy is a set of sensors, most important, a pair of stereo cameras. There are also distance sensors, encoders on each wheel, and inertial measurement units. Fusing data of this sensor, the rover control system is able to detect obstacles and hazards, to estimate the vehicle position and heading, to deploy the arm, avoiding collision, the arm and all its payload, avoiding collision with terrain and the robot itself. Especially, the robot is able to replan in real time its path, its trajectory in case of obstacles, unpredicted or unexpected obstacles. I'm going to skip these slides. They are not so simple to understand and to explain. Just I wanted to highlight the role of the first step of the design of a complex control system like the one of the robot. The first step concerns defining the control function, the function that the control system must implement, must perform. The question to this phase would be what control function has to be performed and how well. I don't have time to deal with this topic. I just want to highlight this topic because at university, for instance, we teach very well in engineering courses how to design hardware, the hardware architecture, the hardware of the control system, how to design and develop the software of the control system, but never say something about this important phase, the first step concerning defining what the robot has to do. I'd like to mention an ESA methodology to support this phase called control development methodology, actually to be robot control development methodology that ESA developed a few years ago. Just a few words about the hardware architecture. You have seen there are a number of CPU in a rover, in its subsystems, and they are connected through data bus and data network. Exactly in the same way are the for instance, avionics avionics systems are. The CPU are the same we can find in our computer, or better, we could find years ago in our computers. They must be radiation hardened microprocessor and memory, not to have faults due to cosmic rays and other radiations. And another interesting topic is concern the electric power system, but I'm going to skip it now. Just a few words about software taken from JPL documentation. Concerning the Curiosity case, the software code was written by a team of about 35 developers at JPL, about 3 million lines of code. Most of this code is C code. Small portions related to the navigation part are in C++, compared with the software in Viking and Pathfinder. And finally, the most challenging and demanding software part in present and future mission are those that concern vision processing, planning and real-time replanning algorithms, and simultaneous localization and mapping. Okay, time is over, and I now pass the floor to my former colleagues, Dr. Edoardo Re, Galileo. He will show you how they developed and how it works, a real object, a real payload now flying to a comet.
Okay.
Thank you.
Thank you very much, Gian Antonio, for the introduction. Okay, I work at Selex ES in Nerviano, and okay, I will show you the development we did for a small spatial robot that we did at the beginning of 2000 for the mission to the comet Churyumov-Gerasimenko. The mission is called Rosetta, everyone knows. Okay, the spacecraft was launched in 2004 with an Ariane 5, and we'll do a global mapping of the comet next year. And the spacecraft has on board a small lander, about 100 kilogram lander, and this lander includes all the instruments that can do their work, their analysis, only by using the samples that we will deliver to the instruments, or in direct contact their own with the comet soil. So the lander is a very important part of the spacecraft, and on board this lander there is this drill that we called SD2. Why SD2? Is okay. The name derives from the part that is drill, the comet soil, that is the first D. Then collect small samples, that is the S, and the samples are some tens of cubic millimeter, and then distribute, it is the second D, the samples to the instruments on board the lander. While this has been a very challenging project for us, because you can imagine that after 10 years, the spacecraft should work and should be completely autonomous because of the time needed to command the spacecraft from the Earth is too long, and so it has to be completely autonomous. And above all, there is little power, because the power is generated, is granted by the batteries on board the lander and the small solar arrays, but it is very limited, and so we had to do with very low power electronics. There is also a very big constraints in terms of mass. The mass available for the complete system was very low, and the system was supposed to be capable to operate at very, very low temperature of minus 160 degrees. And this is very, very difficult to obtain, because you can design something that can work correctly and fine at ambient temperature, but then when you go to this very low temperature, you must imagine that it's completely different. So this employs a complete, let's say, thermomechanical design, that when you go from 20 degrees, when you assemble the things, to minus 160, it has to operate. Of course, the autonomy in operation and the 10 years in orbit that can create a lot of problems, for example, cold welding. So you are obliged to choose the proper material that avoids that the material sticks between one and the other during this cruise phase. So how is done the drill? The small robot consists of a drill, what we call drill box, that is the vertical column you see, and below this column there is a carousel. The carousel is equipped with small ovens, with small yes, ovens where we deposit the samples that we collect onto the comet soil. And then the system is completed with control electronics, is about 1 kilogram diesel electronics, which includes the digital processing unit and also the boards for the motor control and the sensor management and so on. Of course, inside the unit there is the embedded control software. How can we get the sample? So the drill is equipped with a drill rod that is about 60 centimeters in length. So virtually we can take sample up to, let's say, depth of 50 centimeters, but the spacecraft will be normally about 25 centimeters, 30 centimeters above the soil, so that we will collect the sample at about 25 centimeters in depth. The rod is 12 millimeters in diameter, but you can see in the central picture there is a small tube which can be protruded from the rod when you have to collect a sample. So normally this small tube is inside the rod, you see on the picture on the left. When we want to collect the sample, the tube is extracted from the roil, then we continue to drilling and the small tube entraps the material. And the material stays there because of the adhesion of the material to the tube itself. So you see on the left the tube extracted during a testing we made, and with the drill, on the auger of the drill you can see some material that was originated by drilling the simulant of the comet soil. Okay. When the sample is entrapped, then we discharge the sample in the ovens. You see on the left some ovens accommodated on the carousel. The carousel has 26 ovens. Why these ovens are something special? Because, for example, the ones on the left of the picture is an oven that can allow the inspection by a microscope. So you deposit the sample in the oven, in the cylinder you see on the top of the ovens, but the microscope on the side can see the sample deposited through a special prism made of sapphire, which can present the sample to the microscope. The other oven that you see in the middle are more simple, but as well sophisticated, because they can be heated up to 800 degrees to allow evolving gas from the sample and take the gas to the gas sample analyzer on board the lander. Also the oven with the sapphire can be heated, but up to 200 degrees. When the sample is put within the oven, then you have to close the top of the oven, and there are two tapping stations which put the cover on the oven, and then after that you can heat up the sample to evolve this gas. Okay. As far as the electronics, this is composed of a common digital processing unit and 3 boards for the motor control and sensors. What we do with the electronics, we execute the commands that we receive from the lander, we read the sensor, and of course we command all the motors. But most of all, we make the checks before executing a mechanical command, because if we move a motor and the other part of the mechanism is not in the right place, we risk to destroy the mechanism. And so we have to do a lot of checks on the position of the different parts before executing a command. And then we can have some corrective actions in case something goes wrong. And then we can send telemetry to the lander control and then to the Earth via the orbiter. Okay, just a few slides concerning some pictures on the other. We made at the beginning some breadboards, some small limited parts. For example, the drill tool, we made 2-3 breadboards to check that was effectively working. The ovens, Of course, the motor, because you can buy a motor, but then buying a motor that can work at minus 160 degrees without lubrication is not so simple. So there were special designed motors. And also we made the testing on the carbon fiber parts, which makes the structure of the drill. Then an engineering qualification model was fully tested with functional test, vibration test, and thermal vacuum test with sample collection. And then, of course, the electromagnetic compatibility test, because our system has not to disturb the other system, and it has to work when the other system can disturb it. And, of course, the flight model, where we did the same test of the qualification model, but without a sampling test, not to make the drill dirty from the stuff from Earth. This picture shows some results of the thermal vacuum test. You see the oven with, difficult to see, but this oven was completely filled with our sample. We made 14 thermal cycles in the range from minus 50 to minus 140, and the picture on the right shows that we did the drilling in 6-7 minutes with the 10 Newton thrust employed. And at the end, the collection of the sample is the spike you see on the right of the picture. We made testing collecting 7 different samples in different materials. Okay, and of course we hope that next year the mission will be successful after this 10 years journey. Okay, we all hope that.
And we invite all of you next year on November to be here. And we will tell you what we are doing on the comet, because this is a scenario we'll see, the lander on the comet, the orbiter around the comet, and here, and we, you all here in Politecnico di Milano. Thank you.
Personal question. Can you elaborate on how much of the PD2 technology has been transferred to the ExoMars drill that's currently being developed?
Yes. Okay, the basic technology was really developed at the beginning of 90, when we made some studies funded by ESA that were devoted to a very large mission to the common nucleus for the Rosetta mission, and we made drills up to 10 centimeters in diameter, 1 meter length, where we developed the PCD technology for the bits and so on. And that is, let's say, the origin of this drill, that is, let's say, 1,000 less in dimension, if you like. But basically, the technology of drill is transferred to the ExoMars mission, including the capability to collect the sample that is really originated from the original study we made for CNSR. But okay, it's the ExoMars mission is the natural follow-on of this mission for all what concern, for example, the autonomy and also the capability to work in low temperature without with very low power to heat the motors and so on. So basically, a lot of the technology is transferred to there.
Okay, wonderful. Thank you very much. I will now pass the floor to your audience in Milan. Are there any questions from the audience in Milano?
Good morning, and these days we are seeing NASA doing testing with laser communication with a satellite around the moon. In the start of your presentation, you say that we have some problem with the communication. This laser testing can be available also for Mars, and where this improved bandwidth can help, if only with the data transmission, or maybe also for almost real-time control of the rovers.
I'm not an expert in communication, in telecommunication. I asked advice to my colleagues of my department. I think that nothing can be done to reduce the latency of the communication, because it's related to the time the light takes to go from Earth to Mars. So I don't think using a laser we can improve the speed of the light. Such a condition prevents from any kind of teleoperation of the robot. So you cannot control something that answers to your commands with a delay of, depends on the day of the year, between 8 and 42 minutes. Also, you don't have time to intervene in case of unexpected faults or events. So there is no way using relay satellite or laser or any kind of. You must rely on the autonomy capability of the robot. Is the working? Okay, thank you.
Non ho sentito niente.
Here?
Good morning, everyone. I don't know if any of you have heard now about the Mars One initiative, in which a private Holland company is trying to recruit people to send to Mars on a one-way trip to create a colony in 2023. Now, I wonder if this initiative is successful, will it be possible to ask these people to man our rovers for scientific missions?
I knew a lot of astronauts, but I never find one of them that is enthusiastic to remain in space. They always want to come back to the Earth. I don't know why, because that means that if we send a group of people to Mars, they have to stay on Mars and to pass. There are some projects in this sense, there are. But of course the presence of a human on a distant planet is very important, just to work with a robot. In my opinion, the future is a cooperation between a crew and a robotic solution. That will be probably more easy to be done on the moon, because the moon is so close that in 2 days you can go and 2 days you can come back. 3 days. And not for Mars, because Mars is very, very far away.
I think we have no more questions here from Milano.
Okay, thank you very much for those nice questions. I would like to turn the floor now to Technical University of München in Germany. Do you have any questions for the presenters in Milan?
I think there are no questions here.
Thank you very much. I would now like to give the floor to the Hebrew University in Jerusalem. Do you have any questions for the first presentation?
Thank you. Good morning. I wanted to ask about curiosity in Mars. So we know that there is a trace of water there. So I wanted to ask if curiosity is have the possibility to control or to see if there is methane in Mars, so we can improve life in the past in Mars. Thanks.
Non ho capito niente.
I don't know how to use methane on Mars, but what I am sure is that when we have a colony on a distant planet, we can use it as the maximum, because the mission is so expensive that you have to optimize it. We found methane on Titan, but Titan is very, very far away because it is a satellite of Saturn. That means it is so far away we can't do it. But in any case, I always come back to the moon. The moon can be really a celestial body that we can use for metals, for all things that we can find it, even if our interest on the moon is not just to use it, but to understand something about the moon itself and probably the Earth, about which we don't know practically nothing.
Are there any more questions from Jerusalem?
At what stages do you have to switch from autonomous operation by the robot on Mars to a situation where a human controls the system? So what is the limit of the robotic system that operates on the Mars rovers now?
My colleague should answer this question, but I told you that a robot is another myself, an alter ego. Generally,
I suggest to postpone the answer after the presentation of Alina Bouchard.
My colleague suggested to postpone this question after the next presentation, but what I wanted to say is that it is not sure that my alter ego exactly obey what I ask, because generally he has a lot of limits, probably limits connected to the environment, the strange environment in which he is working. That means I can ask him to overtake every obstacle he finds, to do what I call. But in any case, it is a very good support.
Are there further questions from the Hebrew University in Jerusalem?
No, there's no more questions. Thank you very much.
Thank you very much. Then I suggest a large round of applause for a fantastic lecture this morning. Thank you for starting the show so well. Much appreciated. Next up this morning is a presentation from Professor Alin Albouchefer. Professor Albouchefer is currently the head of the Institute of Robotics and Mechatronics at the German Aerospace Center, DLR, and is also professor at the Technical University of Munich. The DLR Robotics Institute is arguably one of the largest and world-renowned laboratories in the field of space robotics. But his personal preference has geared his research towards robot design, modeling and control, non-linear systems, flexible joints, and variable compliance robots, to name but a few. In recognition of Professor Albouchefer's pioneering work, his academic awards include the several Best Paper Awards granted at international conferences, including the prestigious Institute of Electrical and Electronic Engineers King Sun Fu Best Paper Prize. Professor Albouchefer is also the proud recipient of the DLR Science Award. Today, Professor Alin Albouchefer, thank you so much for joining us and talking to us about the cutting-edge research currently ongoing in the field of space robotics and enlightening us on what the future of robotics holds. Your presentation rights will be given immediately, and you may begin when you're ready.
Yes, hello everybody. I would like to welcome you here to our talk in Munich. I would like to thank ESA for organizing this very interesting event. And today I would like to talk about space robotics and particularly the main applications we are focusing on orbit servicing, astronaut assistance, and planetary exploration. But before, I would like to start with an image which kindly was provided to us by the colleagues from ESA, a picture of the automated transfer vehicle. And noticeably, it's not just an automated machine, but it's designers call it a robot. And because it displays some specific robotics properties. And it provides several building block elements for a large variety of orbital vehicles. And it provides the blocks for mobility in space, which will become more and more strategically important in the future. Why is it a robotic or an automated vehicle? Because, as it has been mentioned before, the approaching to the ISS is done based on vision sensors, based on distance sensors, and it's the first vehicle which is autonomously docking to the space station, as it has been previously explained to us by Professor and former astronaut Ulrich Walter. But of course, this started also a debate with my colleagues. What's the difference between an automated system and a robot? And it's not so easy. Even quickly going through Wikipedia, you will find very controversial definitions. And what's a definition bringing together what commonly people think it's a robot, like Honda's Asimo and the automated transfer vehicle. And just grabbing some of the extreme definitions, you see here an industrial one saying a robot is a reprogrammable device, multifunctional manipulator designed to move material, parts, tools, and most importantly, to perform a variety of tasks. This is an industrial point of view, while the more neuroscience point of view related to humanoid robots say robotics is an intelligent connection of perception and action inspired by definition of biological systems which intelligently connect perception and action in neuroscience. So we see the perception is essential, the ability to perceive and make an interpretation of the world, the ability to act in autonomously, but also the multifunctionality. So the difference to an automated system is which just performs the same task is that robots can be reprogrammed to do various tasks. So trying to do our own definition, we could say in a synthetic way, a robot is a technically embodied multifunctional connection of perception and action. And then you can decide yourself what system is a robot and what system is an automated system. And I think ATV is somewhere in the middle, opening really the way to more and more autonomous space missions. But I will focus in my presentation mainly on the three domains we are pushing forward at DLR, and these are on-orbit servicing and planetary exploration, with a particular aspect that we are very much focusing on space robot assistance, of humans interacting with robots. And of course, the main purpose of space robotics is to increase mission success by automating the processes, to enhance space mission capabilities by reducing risks and costs, And since robots are becoming more and more capable, robotic missions get also more and more an interesting alternative for space solutions. But what I would like to point out is that our mission at DLR is not only developing space robotics, but also showing what's the benefit of these technologies for every human on Earth. That's why we are focusing a lot also to transferring this technology to other areas like industrial robotics, medical robotics, electromobility, flying robots. I will give a few examples of results which directly emerged out of the space research at DLR. I will start with on-orbit servicing, and we think that here robotics provides a scalable technology for simple tasks like deorbiting or removal of space debris over more complex aspects as maintenance and repair of satellites. You can see here in the corner an image of a satellite equipped with arms, special tools, but also hands, and having the faraway vision of astronauts helping, or robonauts helping astronauts in their work in extravehicular activities, or even doing autonomously some of these activities. And I will start with the most current application, which is space debris removal. And it's a fact that the number of objects in orbit which are not controlled anymore, so that satellites, upper stages of rockets, is continuously increasing, putting a threat, of course, on the safety of those orbits. Approximately 2 million kilograms of space debris jeopardize manned and unmanned space missions, and there have been at least 2 larger events causing a dramatic increase, as you can see here on this graph, of number of space debris, and depending on different models, it is stated that about 5 to 6 larger objects have to be taken down in the next decades every year in order to keep the threat constant or diminish the threat of having further collision in orbit. And of course, I think robotics provides interesting technology, an interesting alternative to that, because we could design satellites with robotic arms on them, which to approach uncooperative satellites, grasp them, and deorbit them. And just to name two well-known examples, the one is ROSAT, a German satellite, which crashed, actually splashed into the Indian Ocean just 2011. It was a satellite which was not completely burnt in the atmosphere, and of course there was a danger of hitting also habited areas. The next big example is EMBISAT, the largest ESA satellite. It's a 9-ton satellite which is not operative since 2012, and there are a lot of discussions about to take back EMBISAT. For some reason, my slides are not switching anymore. Okay. In our institute, we have a long tradition in space robotics, and the very first robot teleoperated in space back in '93 was launched and operated by DLR. And you see, at that time, we already demonstrated things like recognizing an object, free-flying object in the space shuttle, and grasping it, teleoperation from ground. We had several activities contributing also to the first outside teleoperated system from the Japanese colleagues from JAXA. And of course, in the last 1.5 to 2 decades, the number of robotic arms increased in space, and most noticeably probably the Canadarm, but also newly the Japanese arm. These are large structures doing mainly pick-and-place manipulation operation of large payloads. Also this very impressive application of giving an astronaut the possibility to move around, to have a fixed base in operation on the ISS, and I think it was also with a shuttle. But they are mainly operated manually by joystick by the astronauts. They have limited ability in autonomy so far. So there's a lot of room for improvement for the future. What we did at DLR is developing, following a change of paradigm in robotic design, from these large, rigid position control systems to lightweight, compliant, and adaptable. And therefore, we coined the name soft robotics. What do we mean by soft robotics? Humans are not very precise in positioning objects, but we are relying on vision, we are relying on our compliance of the sense of touch, and we get the precision by in interaction by the measurement of the interaction parameters. For example, you can take the robot by the arm, you can teach some trajectories, you can program the stiffness, the compliance with which it should interact the environment to limit the forces, and most important, you can prove that using those sensor technologies, those robots are not dangerous to humans. Even with this kind of very extreme experiments, you can show that the robot, even in the worst case, will not harm a human. And this opens, of course, entirely new possibilities. And out of this prototype, then we follow different directions. We sold this technology to a terrestrial company. I thought it's an important aspect to us, to the company KUKA here in Augsburg, close to Munich, which is the second largest robot manufacturer. We developed robots for medical application. We developed our humanoid Justin for studying autonomy aspects as precursor for space missions. But most importantly, we developed this technology towards space qualification, and we had a German mission called ROCKWIZ starting in 2004 and operating until 2011, where joints of these robots have been mounted on the International Space Station. You can see here the mounting by the astronauts, and for the first time we demonstrated that it's possible to teleoperate from ground with a force feedback device. That means that the teleoperator can also feel the interaction forces measured by those torque sensors. You can operate with a direct link this robot on the space station, and on the left side you can see some of the images when the robot performs several tasks, even teleoperated from the home of our system engineer from his laptop. He could start the system doing operations, for example, navigation in a labyrinth, pulling springs, and so on. But what's the purpose of this system qualification? In Germany, we plan a large robotic mission, a large robotic demonstration mission called DIOS, and here we will be responsible for vision-based approaches, for the robot design and manipulation, for dynamics control, and for the ground control. And the mission here is to demonstrate both approaching, grasping a non-cooperative satellite, stabilizing it, then demonstrating several prototypical service and repair activities, and at the end perform a deorbit of both satellites in a controlled manner. Therefore, of course, we have testing facilities to simulate the approaching, but you also need to know how the influence of a moving robotic arm on a satellite will be. Because of the conservation of momentum, the move of the arm will disturb the satellite, and using two independent robots which can be controlled in such a way to simulate the free-floating motion, you can test all the software on ground as it would as it would happen in space. You can see here the mission, the prime for this mission is Astrium. They are designing the satellites, they are designing the whole mission, and you can see here the test setup at DLR. This is an example how moving the arm, you see a disturbance on the satellite, and you need to take this disturbance in account. The way it is done is that the satellite is placed on a force torque sensor, which is connected to the robot. As soon as you feel some forces in this sensor, you can use a simulation of the free-floating dynamics, and the robot will move the satellite in a way it will really move in space. The next thing is just to show that the robot is really free-floating. You can pull on some strings, and then indeed the satellite starts a translational motion, which is an arbitrary motion, so it's just commanded by my colleague over here. And then in the next stage, I will jump in a further stage of the video. You see in the next stage, the robot is approaching, is using vision system in the final setup to track the free-floating robot, is tracking the motion, and at a certain point we start the grasping command, and then the robot will be grasped and stabilized. And because of these compliance properties, you can see that even when the velocity of the satellite is high, such that you will have an impact between the satellite and the robot, the system is able to cope with these accidental contacts due to the compliance of the system. And now the grasping command is initiated. The robot grasps the satellite and stabilizes the relative motion. In the next step, the satellite will be fixed by a fixture system, and the robot can do servicing operations. We designed for ESA also a humanoid arm, and to my knowledge is the first humanoid arm, or humanoid hand, sorry. The arm comes from the Italian colleagues. The humanoid is the first humanoid hand designed for outer space mission. It can be again teleoperated by a data glove, and we have a request now from American colleagues from DARPA for using this hand also in an on-orbit servicing mission. It is a very interesting space robotics mission where the goal is to use a satellite with 2 robotic arms which should go to graveyard, pick some of the components of dead satellites, in particular the large antennas, bring them back to geostationary orbit and place new electronic modules on that. And as one of the most advanced tools, we will send our DEX hand in order to manipulate flexible elements, cables, and the coverage of these antennas. As a combination of hands and arms, there are several very advanced systems, and one of the well-known is NASA Robonaut. There is one Robonaut on the ISS. This was a visit I had in Houston to the NASA colleagues some years ago, and we are working strongly towards developing also the autonomy capabilities to have true astronauts helpers in form of humanoid robots. This is our development at DLR. This is our humanoid robot. You will see always the same modules because our robotic concept is a modular one. Joints have self-contained electronics, actuators, sensors, such that you can use those modules, meanwhile provided by our industrial partner, to build up more and more complex systems. And you can see here some of the features the system have. You have vision in order to recognize objects, to grasp objects. In order to imitate the human motion, there are several motion capturing devices. Still is the best tool, or one of the good ways to try to understand human motion and then transfer it to the robotic system. And we are also focusing on locomotion on difficult terrain. Of course, we would like to have the robots not working only on flat ground as today, but working on difficult terrain as we would encounter on Moon, on Mars, and being able to balance and stabilize the walking body on difficult terrain is a key feature we are working on. So far, the compliance we had in the systems was one controlled by software, while the robots are still rigid by themselves. In an impact, the former robots would be destroyed. That's why we are trying to get inspired by human musculoskeletal system and insert compliance into the system itself. And then you can do things like really hard impacts. So we would like to have robots which can fall down in case of failure. You know, you see here the mechanical designer hitting his own robot with an acceleration of 200 G, just to demonstrate that such a robot can withstand hard impacts. But in order to do that, you need a mechanical intrinsical compliance. Humans have this kind of compliance. Human muscles, human tendons are compliant by themselves. By having an antagonistic muscle system, you can co-contract those muscles and increase the stiffness. So what we did by software so far can be done in a hardware manner. And then you can not only increase robustness, but also increase performance, as seen in this video, for example, for doing fast motions. In this case, one robot throws the ball, the other one uses his cameras and catches the ball. This is just a way of developing technologies and demonstrate that fast motion, fast vision, fast ability to catch flying systems can be handled today. And all these technologies are then required and transfers to space applications. So to summarize, we have two waves, technological waves. The first one is the torque-controlled, meanwhile, in my opinion, very mature technology for which, on which we are based when we are designing our space robots for the DEOS mission, the DEX hand, and our larger humanoids. On the other side, we are trying to go even closer to the biological inspiration source by using intrinsic compliance. And there's also, I think, a very interesting scientific challenge of understanding human motion principles to build even better robots. In terms of operation, on one side, we operate the robots autonomously. And here you see two examples. We started this drawing and catching ball example just because we said as soon as we will be able to demonstrate on Earth something like that, everybody should believe that we have the technology to grasp and stabilize satellites as well. On the other side is the difficulty of doing planning, and again here the dual use, our robonauts demonstrated in everyday service scenario, but the ability to use sensors, planning to recognize its environment, it's common no matter what application you have for the robotic systems. And the ability to control a flexible, complex arm on a mobile base. We started developing it first for terrestrial applications. Now we transfer this technology from the mobile base on a fixed ground to the mobile base of a satellite, as seen before for the DEOS mission, but exactly the same technology which you need. Compliant manipulation, dynamic interaction of the robot with a basis, online image processing, autonomous planning. You use also in terrestrial environments, and I think this is the first application where you have a helicopter with a robotic arm able to grasp objects. This is even more complicated than for the satellite because the dynamics of the satellite is well known, while for a helicopter you have complex aerodynamic effects, ground effects, requiring the robot to stabilize the oscillation motion of the helicopter. I mentioned the aspects of safety, and in order to have robonauts helping astronauts, we needed to develop the technology, but also the qualification technology to show that a robot is safe. Probably you all know Isaac Asimov's literature and his famous 3 laws. The first saying a robot should never hurt a human being. It's of course a prerequisite for human-robot cooperation, but it took a lot of time to develop the technologies and the validation to show that indeed a robot can help an astronaut in its daily use. And we use the robots in 2 ways. In one way is autonomous. The second way is in teleoperation. And here you see you have a remote system which has a stereo camera pair. The operator sees the stereo image but is attached to the robot through which he can command the motions to the robonaut. On the other side, because the robotic system has torque sensing, the person can also feel the interaction forces. This is very important for assembly tasks, for example. Here we can see a demonstration of a typical environment which you would encounter in repairing a satellite. You need to uncover the system with this flexible structure, then unscrew some elements. So a typical repair and servicing task, which would not be possible just by transferring the image, but you need to measure and feel the interaction forces, which is a challenge as soon as you have long communication delays. But today we are able to communicate and teleoperate to any point of Earth with a good internet connection and to orbits where the communication is below 1 second. Again, the dual use aspect, we developed this technology for teleoperation in space, but it's equally used, for example, for medical applications and for industrial applications. Medical application is surgery on teleoperated surgery using medical robotics is an increasing area because it can improve the precision, it can reduce the complications of an operation, or maintenance and repair of nuclear, offshore, and dangerous plants. You can use exactly the same teleoperation technology, the same robotics technology, with the only difference, of course, that for space you have the harsh requirements. We have heard from Professor Magnani and the colleagues in Italy. You have to do qualification down to minus 100, 150 degrees, and very harsh temperature and radiation conditions. But what's the future of teleoperation? Not only operating the robots by using other robots as input devices, but we are doing studies now on teleoperation using muscle currents, EMG measurements, and even a teleoperation with colleagues in US, where a brain interface has been used to, in this case, by a paralyzed person to control the robot arm, and for the first time she was able to grasp with it and with this interface to grasp the bottle and drink from the bottle. So the future of teleoperation could be that we will control our robots by toe. Now back to the missions we are preparing. In 2014 we plan to send such a force feedback device to the International Space Station. In this case it's a cooperation with the Russian colleagues. We demonstrated the operation from ground. Now we will provide the astronauts with this capability of using force feedback input devices, in this case a joystick. What's the motivation behind? If we think about Mars missions in future, human Mars missions as well, probably the first step is to send humans just to the orbit, as it has been done on Moon, because there's a huge increase of cost if you want to send the humans to the surface, and then you would have the small latency required to teleoperate robots on the surface of the planet or on the surface of the Moon with high precision to do, for example, assembly of a habitat environment. So we will demonstrate this mission, and then we have a second mission together with ESA. The mission is initiated by ESA and is called Meteoron, about placing an exoskeleton, transporting it to the International Space Station and setting up the technological framework, the infrastructure, to allow astronauts again to telemanipulate in every orbit or on the surface of the planet robots by force feedback input devices. The application is, of course, challenging. From time to time, my application stuck. I'm sorry for that. I need some help again, maybe. Okay, you can see here that the task of telemanipulating the system from ground is somewhat difficult, because you are using several antennas distributing on the Earth. We would like to have a direct connection, to have a minimal delay of about 10, 15, 20 milliseconds. In this case, we will have an antenna in Germany, one in Sweden, one in Russia, and the data will be switched over the different relays. You will have the direct data from the satellite to the antenna, then sending it to the teleoperation site, and this requires substantial infrastructure, which we plan to build up with this technology, for this technology. Just to summarize on one slide, what's the benefit on Earth from these applications? Robots which interact with humans are interesting not only for astronauts, but also for automation of factory assembly. For example, Daimler will use these interactive robots to do assembly in car manufacturing jointly by humans and robots. And I mentioned these medical applications. The surgeon has the possibility to interact with the robot to prepare the operation, and then the robot is used in teleoperation modes. There the barrier is not a distance, but the size, the human body. The surgeon can do large motions in teleoperation. The robots will do inside the body very, very small motion. Finally, I would like to come to the exploration topic. And here again, we see a development from the today rover systems. Here you can see a prototype of the ESA ExoMars, to more and more complex systems. And we are researching now on systems which are able to go not on even terrain or on limited slope, but to go on really steep slope and difficult terrain, because usually geologists or paleontologists go to places where you have direct access basically to the whole history of the geology of the planet. We are researching on teams of collaborating robots, having even heterogeneous robots to do efficient exploration. And of course, the faraway vision is as soon as we will have maybe humanoids on, or humans on Mars, astronauts on Mars, I'm convinced that at that time we will have also humanoids, robots, helping them or even going ahead and preparing habitats. But back to the current state, of course, NASA sets the state of the art with its very, very successful Mars missions. We heard about this, so I won't go into detail. They started in 1997 with the Sojourner, and the size and the complexity increased over the time, and now Curiosity landed and is doing operations since 1 year. ESA has also a project which the launch has been delayed, but hopefully we'll have also a European system landing and doing experiments on Mars. And there is, in the autonomy, there are still many, many challenges. And for example, one of the NASA rovers had to be stopped because it got stuck into the sand. So we have several test facilities where we analyze the behavior, the terra mechanics, the interaction between the wheels and the sand. We develop the control strategies to optimally interact even in difficult terrain. And this is an experiment, for example, done in preparation for ESA's ExoMars mission at DLR. We are also focusing, as I mentioned, on different mobility concepts, not only wheels, but wheels and legs for going to difficult terrain. And on this animation over here, you can see, in some sense, exotic approach. It's a very minimalistic approach of an instrument we will deploy on an asteroid. It's within the JAXA mission, and Germany has a small payload called Mascot. We have here only 200 grams available to move the system on the surface of the planet, and we use therefore a simple eccentric system to provide an impulse to the robotic system. The difficulty there is that the robot, or the gravity of the system is very, very low. I will say a few words later on that. So you need to do very precise control on the system. What those robots are still missing, and we are also researching on, is a high level of autonomy. What we would like is to be able to just point in the image to a certain place the robot should go, and then the robot should completely autonomously follow its way there using stereo camera pairs, other sensor systems. And we are also interested in teams of heterogeneous robots cooperating to complete the mission. For example, of course, you have wheeled systems which can carry large payloads and are very stable, but in order to get to some areas which are difficult to reach, you will need legs. And at least on Earth, we can use flying systems. There are some research to do flying systems on Mars as well, but of course, because of the thin atmosphere, there are some strong limitations. But here we are researching about how to integrate those informations, how to build online a map of the environment, to check the affordability of different trajectories. Red areas are dangerous for the robot. Green areas can be chosen for a given trajectory. And at the end, we would like to have systems of robots which provide, for example, in this case, a flying system giving the overview, the mobile system deploying the payload, so provide their capabilities to joint completion of tasks. We have a large mission in Germany called ROBEX, and here again we are developing the infrastructure. It's a study in view of a possible lunar mission. This is about deploying several scientific instruments on the moon and connecting them through a network in order to gather data and have a robotic system to do the maintenance of those measurement payloads. I mentioned the Mascot mission. The start will be in 2014, so we are doing the final qualification test this year. And I mentioned that the difficulty there is with a weight of just a few kilograms, including the payload in the instruments, to have a system which hops around the asteroid and do measurements at several points. The difficulty is that gravity on this asteroid is 10 to the minus 5 G, and you need to very precisely plan and control the motion in order to not exceed the escape velocity, which is less than 30 centimeters per second. We did a lot of testing on ground, but it's very difficult actually to create on ground an environment with 10 to the minus 5 G. Even to parabolic flights, you have the order of 10 to minus 3, or in the towers, you have just very short time. So it will be a very challenging and interesting mission. And I would like to finish my presentation again by showing the transfer technologies potential of space technology. In this case, for exploration, you have seen here the Mars rover, and we developed, based on the same technology, a prototype for an electric car, a specific design of electric car, a car which can turn in place, which can park sideways. It's exactly the same technology we use for the rovers and the same way of controlling the robots, because Mars rovers have the same abilities of doing, for example, rotations in place. So they have much higher maneuverability than classical robots. And on the other side, the imaging technology we developed for processing images on Mars and processing also the environment of the robots now were transferred, for example, to Daimler-Benz. And if you know this commercial, so people watching German television probably will know this commercial. It's advertising the new collision avoidance of the Mercedes cars. And this uses image processing and image processing, online 3D image processing algorithms, which we first developed for autonomous robots for space exploration. So I would like to conclude my talk by summarizing that space is an exciting field of activity by itself, but also is very beneficial to society by its many spin-offs which are directly transferred to terrestrial products. Thank you very much for your attention.
Fantastic overview of space robotics and certainly Earth applications also. I would like to start off the questions and answer session. I do have a question for you, and perhaps you would like to comment on the differences in haptic feedback in 0G versus 1G and how DLR tries to investigate these discrepancies.
Of course, we have now quite long experience on haptic feedback on Earth. What we do not exactly know is, on the first, I mean, there are several ergonomic aspects which we would like to investigate, right? A very, very simple question, you need to somehow fixate the astronaut. Of course, having a force feedback device which would apply some forces on the astronauts will cause the astronauts to move to the space station, what you would definitely not want to have. So the question is how you can make a working environment which is comfortable for the astronaut. What are the force levels which are comfortable for the astronauts? Of course, the human body in 0G adapts to these conditions, so there is a completely different behavior. This is one aspect, the ergonomical aspect. The other one is a very technological one. As you have seen, you have a lot of communication infrastructure which you need to set up. And in order to do high-performance force feedback teleoperation, you need short time delays. So, of course, we have a lot of communication satellites all around the Earth, but if you would like to go to time delays below 1 second, there's not much infrastructure available. So the goal of this project is also setting up the infrastructure to make this kind of teleoperated activity ubiquitous in space.
Wonderful, thank you very much. I pass the floor to the Technical University of München. Are there any questions in your audience?
Maybe you come to the front.
Okay. If I understood correctly, the DEOS mission brings its own target up to space, and I would like to know what the timeline or the roadmap is for using the DEOS system on a real satellite rescue or maintenance mission.
Yes. Indeed, we sent 2 satellites, and the reason is that we want to test a broad range of technologies. So we will have a target satellite, which you, at the first experiment, it will be stabilized. So it will be the simpler task of attaching us to the ISS. Then you can start rotating this satellite to spin it around one axis. Then you can have this tumbling, so the real behavior of an uncooperative target. So you have the possibility to place it in different states and experiment these technologies under various conditions. And then probably the most interesting target today from European perspective is ENVISAT. And just this year it has been issued a call for studies for deorbiting ENVISAT. Of course, there's a competition between different concepts. There's a net concept throwing like kind of a fisher net around the satellite. There's a concept with tentacles, and there's the robotic concept. And there's not a clear time frame yet when to take ENVISAT back, but we think about probably time frame about 5, 6, 7 years, something like that. It is a danger for the orbit, so Europe needs to handle or to be active in this direction. And hopefully robotics will make the run. And I'm arguing for robotics because robotics is scalable. So you can deorbit systems, but you can also repair them.
Thank you.
But maybe Dr. Solanzo from ESA can also comment a little bit on that. So because ESA is really the one pushing towards an ENVISAT solution.
Yes, I certainly can confirm that this is one of the most challenging activities within the European Space Agency to try to recover or to get the satellite back away from the orbit. But ESA is working with lots of organizations, including yours, and we are pushing forward to get the best technology, the best investments in research and development for that. So we thank you for all the efforts that are being made at the universities themselves and at the other research and industrial centers all over Europe.
Thank you. There's been another question back there, I think.
Hello, I have also a question. How will you solve the problem to grasp a real satellite? Because you use for DEOS real, but you don't have it on a real satellite. So how want to solve this problem?
The question was how to choose the grasping points. And this is, in preparing the ENVISAT study, this was one of the really challenging and very, very interesting questions, because ENVISAT is a heavy satellite, and in order to deorbit it, the estimation is that one would need about 1.3, 1.4 kilonewtons of thrust for deorbiting. So you need a structure which is strong enough to withstand these forces. And we analyzed ENVISAT in particular, and there are some places. Indeed, there is this kind of a ring which is used for attaching the satellite to the rocket and in the start phase, but unfortunately for ENVISAT, it is occluded by the solar panels. So this place cannot be grasped by the robotic system. But we identified 2 or 3 points where we think we can do it. It's, for example, the structure supporting the solar panels. It's one of them, and there are 1 or 2 further points. So usually there's a hook where the satellites are attached during transportation. So there are several points which are strong enough to enable grasping. I think we have no further questions here in Munich.
Okay, thank you very much for those very nice questions. I would like to pass the floor now to the Hebrew University in Jerusalem. Do your students and audience have any questions for Professor Al-Bouchefa?
During your presentation, you showed how the robotic arms or other things could do really amazing things and help, important fields like robotics or perhaps, stuff like that. But when do you think, robotic things like that could be moved into the lifestyle of people in everyday lives? Like, do you think it will happen? And if you do, when do you think it will happen?
That's a difficult question, and I will be cautious in answering it because we were hoping to have robots, for example, in many industrial environments like 10 years ago. But what is really a fact is that industrial robotics is very widely spread, and now we have a next step. I would even say a revolution in robotics in the sense that robots leave today the cages of the industrial setups where everything is well defined, because we have better and better sensors, we have communication, wireless communication, data processing available, such that we start seeing autonomous robots, autonomous vehicles, also due to the progress on algorithmic side, for example, for simultaneous localization and mapping of environments. Well, you can call it a robot or not, but there are a lot of cleaning systems, also for grass cutting, for example. There are several robots which found their way to the households. The next area is medical and healthcare. And there is one American system today on the market used mainly for prosthetic operations, but it seems to be a really huge market, a billion market, and we also succeeded to license our technology to a possible competitor in the medical area. So in the next decade, we definitely will see an increase of robotic systems in healthcare and medical areas. Really, the home robot is probably one of the most challenging applications because we have very strong cost constraints. You can ask yourself, how much would you like to pay for such a robotic system? I tell you today, you should pay several 10,000s of euro. Probably you would not like to do that. And on the other side, the environment is very, very unstructured. So the difference between an industrial environment where you can very precisely define where objects have to be, and a home environment, which are different from household to household, is huge. So you have large challenging in terms of perception, autonomy, and adaptability on one side, strong cost constraints. So probably the development will be, going from areas as industry and space through medical, healthcare, professional services, and then at the end of the story, we will have the personal robots, I would say in a range of maybe 15 years. Not a humanoid in 15 years, of course. I see Darius Bushka, who is a professor working on image processing, and he knows how difficult it is to recognize objects in any lighting conditions in unstructured environments. So this is one of the big challenges we still face today. Thank you.
Are there any further questions from Jerusalem?
Yeah, I have one. Is it possible to use a robot to get out of the space station, for example, and fix something outside? And if it is possible, how do you prevent it from freezing?
Prevent it? I'm sorry, from what?
From freezing.
Freezing? Okay. So indeed, this is one possible application we are very seriously thinking of, because if you are familiar to these AVA activities, is similar like going to deep water, because there's a difference of pressure, so the astronauts need to be prepared over several hours. There's of course a high risk, and so there's a large difference between operating inside the ISS and going outside. And having a robotic system which can do these operations, the simple ones autonomously, the complicated one teleoperated by the astronauts from inside or even by operators from ground, would be very helpful. And this is the reason why NASA is developing the Robonaut, why we are developing robotic systems. There are several steps towards this, and we will qualify some of these technologies in DEOS. So far, there is well, people are very cautious on doing this kind of experiments on ISS because of safety regulations. So we just heard from Professor Walter an accident which happened on the Mir, I think two decades ago. If you have a system bumping into the space station and causing a hole, this has a very dangerous effect. So probably we will test this technology first on spare satellites, which would not put humans in danger. And the next step will be to go to the space station. And there is a lot of discussion going on what happens after the ISS. And I hope that the assembly of the next large space structure will not require as many AVAs as the ISS required. So that's a very essential point. About the freezing, this is not the largest challenge. As long as you have energy, sufficient energy, you can heat the system. So all these robotic systems have some thermal regulation capability, some heaters starting to heat at minus 20 degrees and stopping to heat or starting to cool as plus 30. And I was amazed. I was participating like 10 years ago to this Rockvis experiment, but as soon as we switched on our system on the ISS, we had always something between minus 30 and plus 30 degrees. So the ISS seems to be large enough to have a thermal capacity such that the temperature does not vary so much over the 90 minutes it needs for a full rotation. So temperature is not such an issue here. Radiation is an issue, of course. You have a high degree of radiation, so you need a lot of redundancy in the electronics to withstand the high radiation over longer time. And the radiation is even worse when you go to deep space, as well as the thermal conditions as well. So this makes space electronics and space hardware really costly and complex to develop indeed.
Thank you very much, Professor Abou-Shefa, for that answer. I would like, in view of the time constraints, move on to Politecnico di Milano. Do we have any questions from Italy? I'm afraid we cannot hear you. Can you repeat your question, please?
We talked about these objects who are orbiting around the Earth, but I think these are not only small objects. If I remember right, we are some part of old rockets which are orbiting around the Earth. Can we handle this problem and we can get rid of this object by using these robots of which we talked about, but in which way can they help us to get rid of this part of objects orbiting around the Earth?
Yes.
Can we destroy them? Can we destroy them or move them back to Earth or something else?
Destroying, it's a dangerous idea, actually. There has been a crash between two satellites, and this produced thousands of smaller space debris components. And as it has mentioned before, those parts move on orbits with 20,000 kilometers per hour. So if they will meet again at some other point of the orbit, the effect is very dangerous. So one should try to take them in one piece down to Earth. That's the only thing you can do. With small debris, there are several concepts still in study stage, even using some very strong lasers from ground to the orbit. But this is for objects in millimeters or centimeter scale, let's say. For large systems like upper stages or MVSAT, MVSAT is, I think, one of the largest bodies, as I mentioned, is about 8 point something, almost 9 tons. You need to approach them by a specific device and bring them down. And yes, you can do it with robots because the spinning velocity is not very large. So the estimation is that they will spin or tumble with a velocity of about 4 degrees per second. So that's not a large kinetic energy. And of course, there's a 9-ton system, but you don't see the weight of the system. So if you grasp it and push it somewhere, it's like, you know, pushing a ship on water. Maybe this is an idea. You can push a ship, a 9-ton ship, on water with your own arm or with your own foot by just constantly pushing for a certain time. So you don't need large forces if the systems are not moving fast. And we did extensive simulation and studies. And you can do it with an arm of fairly reasonable force. So this is not an issue. The issue is probably having a system which is flexible enough to estimate the motion, to detect the grasping point, stabilizing them, and then keeping it firm enough to do the deorbiting, also for entering the atmosphere. Of course, one would like to have technologies which, for NVSAT, we will have a dedicated system because NVSAT is large. But maybe for smaller systems, you would like to have one satellite attaching to different space debris components, some deorbiting mechanism. Kind of drag sail, for example, in low orbits where you have still some atmosphere. You could have a drag sail, kind of a parachute if you want, using the remaining atmosphere to break down the velocity. There are very many concepts trying to use the magnetic field of the Earth. So there are several studies going on, and probably we will, well, sooner or later need to be active, and probably the next big impact when this will happen will trigger these activities. But I think we are quite ready in terms of technology today. The main issue is who will pay for this deorbiting, because there are huge costs related to this issue, and it's a big discussion, political discussion going on, who will take this cost.
Okay, thank you very much, Professor Albu-Schiffer, for this answer. I'm afraid, although I can see that there are questions that are going to discuss quite some discussion, or create quite some discussion, that I'm going to have to cut these questions short due to the time. So thank you once again for a wonderful presentation on space robotics and human interaction and implications on Earth.
Thank you.
Finally, this morning, I have the immense pleasure of introducing Professor Daniel Rosenfeld, who has an illustrious career which began in the 70s as a teaching assistant and subsequently as an instructor at the Department of Atmospheric Sciences in the Hebrew University of Jerusalem. In the 1980s, Professor Rosenfeld went stateside as a research associate in the severe storms branch of the NASA Goddard Space Flight Center. Currently, Professor Rosenfeld is a faculty member at the Hebrew University of Jerusalem in the Institute of Earth Sciences. Professor Rosenfeld is the proud recipient of multiple prestigious awards, here naming but a few: the Werner Suomi Medal of the American Meteorological Society, the Michael Landau Prize for Sciences, the Schaefer Award from the Weather Modification Association, and my personal favorite, the Thunderbird Award of the same association. With a focus on satellite technologies, Professor Rosenfeld, I invite you to discuss the influence of air pollution and cloud coverage and how this impacts the delicate energy budget of planet Earth. I will now provide you with presentation rights, and please commence your presentation when ready.
Hello from Jerusalem. Let's have the presentation online. All right. We are now will move to look at a very precious planet to all of us, planet Earth. And in order to have a good look at it, we have to take step back and look at it from distance, from space, and then amazingly, what kind of things we can observe that we can't really do when we actually stand here on Earth in the whole system. Of course, the proliferation of mankind on Earth has created a large host of environmental problems. Prime of them is the much feared climate change and global warming, and a whole constellation of satellites with very sophisticated measuring instruments have been launched to investigate this problem. I will look at, I will actually now show, why do I have here the wrong, something is wrong here, it is not the right version. No, that's, I'm missing your key slides, sorry. Okay, that's it. The other presentation was a much earlier version, just experimental. So, can we see now the full presentation? Good. Oh, sorry. Please go to the next slide. All right, here we see the complex Earth system and the ingenious ways by which satellite can measure the various properties of the Earth system. We'll see that we can measure all kinds of properties that we have never thought that it is at all possible. For example, the three-dimensional temperature of the Earth system, its winds, the moisture fields, the chemical composition of the atmosphere to a great detail. We'll see how we can do that from space without actually pulling a sample of the atmosphere and measuring its chemical content. And that includes, of course, the constituents that are of most interest to us, which are air pollution, gases, and aerosols and dust. Another set of interestingly important properties are the clouds. We generate the weather and precipitation, the three-dimensional structure of the clouds, the drops and ice particle size, and the size is very important because when the particles are larger, they tend to combine more quickly to form precipitation. And then we can show how we can actually measure the precipitation from space using space-borne radar, measuring the lightning when the precipitation is very intense and form through ice processes. And then we can go down to the surface part of the system, measuring the surface temperature, vegetation type based on their spectral response, and that produces together ecosystems, and we can get specifically and monitoring crop types and health, going to other aspects of the surface, measuring the mineralogical structure and doing geological prospects. We can even monitor what happens below the Earth's surface from space by ground measuring radars. We can get information about the soil moisture, even the amount of groundwater, and ground movements as a synthetic aperture radar can, when we compare different pictures in time, we can see tiny movements by a fraction of the wavelengths of the radar, and that can tell us about building strains in the Earth's crust and actually movements along geological faults. And of course, we can go to the ocean system, measuring the ocean temperature and salinity. How can we taste the seawater from space to see how salty it is? Again, the electrical conductivity of the water is determined by the amount of salt in them, and that can be measured by certain types of radars. We can measure also the biological productivity within the ocean by the color of the ocean, measuring it very precisely, the chlorophyll absorption bands. We can measure the wind speeds by radar measuring the wave heights and directions. And even the ocean heat content, how much heat that comes into the Earth system is stored in the ocean and not hitting directly the atmosphere, and that is because the heated water is expanding and the water sea level rises, and we can measure from space very precisely the rise of the sea surface height, and that tells us what is the heat content of the water. We can measure ice, the ice thickness, both sea ice and the ice on the ice caps. For example, one of the fears, great fears because of global warming is that the polar ice caps will melt, sea level rise, and will flood the coastal cities all over the world. By measuring exactly the topography of the ice caps, we can see the rate of the melting, and indeed we see alarmingly accelerating rate of melting that is actually feed our concerns, and also the initiative to do the research and measurements. So the first weather satellite was launched fairly shortly after the first Sputnik in 1st April 1960. That shows that the measurement of Earth from space has been the priority early on from the time that mankind has learned how to send stuff to space. And here we see the first light of the first weather image, and it is called TIROS-1, which is, TIROS goes for Television Infrared Observation Satellite. A very convenient orbit around space for measuring the Earth is what we call a geostationary orbit, where the satellite rotates around the equator at the same time of the rotation of the Earth in the same direction, so it's practically hanging over the same spots over Earth, and then it can take series of images or pictures and document the evolution of the weather systems. And one very obvious such application is taking time-lapse of the evolution of storm clouds. Now we can take such time-lapse images every 1 minute and project it quickly for a full day. Here is a case of imaging of a cloud system that produced severe storms near the eastern coast of the United States. This image shows a rectangle that we'll see in the next slide with the movie of the literally boiling clouds with a lot of energy. And the dots here, the red dots show where tornadoes occur, green dots are hailstorms, and the blue dots are where damaging winds that did not reach tornado grade occurred. So if we go to the next slide, we see the clouds in action, in motion, and you see how the clouds are literally boiling. The heat from the lower levels goes up violently as strong vertical winds, and you can actually see the atmosphere boiling, and the strong vertical winds actually produce the large clouds, the hail, and the tornadoes and lightning. In the please go back one slide and click it for start. Okay. This is a movie that needs to be okay. So here we see the same cloud system zoomed over the Washington area, and we see the lightning flashes that run through the cloud system in the 1 minute sequence. The sensing of lightning from geostationary orbit is not yet applied. Here we combined the images from satellite with lightning measurement from the surface, but the next generation of the geostationary satellites is going to have the lightning sensor and will be able to see images like that covering all over the world. Next slide, please. Okay, so this is the very basic way of looking at Earth, but we want to look at to measure the constituents of the Earth. As we know, one of the greatest concerns of the global warming is because we spew into the Earth's atmosphere increasing amounts of greenhouse gases, and CO2 is the most important among them. So how can we actually measure the chemical composition of the atmosphere? For this, we rely on the fact that different greenhouse gases are actually having absorption and emission bands in the infrared and solar spectrum that we exploit for the measurements. The graph inset on the lower left part of the slide shows on the abscissa the wavelengths in micron, and on the ordinate the absorptivity of the atmosphere as a function of the wavelengths. In this image we see the thermal image of the Eastern Mediterranean Ocean at 8.5 micron, which is an atmospheric window. It means that the atmosphere is transparent in these wavelengths. So we see the temperature of the surface and the clouds. And the code is such that warmer temperature shows as darker area in this midsummer noon over our part of the world here, the Eastern Mediterranean. So you see that the sea surface is brighter. It means that it is cooler than the sun-heated surface around it. And the clouds are much brighter. It means much colder because they are occurring higher in the atmosphere where it is colder as it becomes colder with the increasing height in the atmosphere. So let's see what happens if we go and look at the same image in absorbing band where the water is slightly absorbing. Okay. Now we no longer see the Earth's surface. We see just the water vapor amount in the atmosphere. And when we have brighter areas, it means that they are colder. It means that they reach greater heights. If we go to an even more absorbing part of the spectrum for the water vapor, we even no longer see the clouds. The clouds are lower or warmer than the water vapor at the top of at the highest part of the atmosphere where water vapor exists. So you can see that by slicing the atmosphere to different elevations with multiple different channels or spectral bands, we can actually get a vertical profile of the content of the water vapor and its temperature. And this way we can map the most important greenhouse gas in the atmosphere, the water vapor, which is also important for the weather. We can do the same for CO2, which is the most important, the man-made greenhouse gas, and to many other constituents. In order to do that, in more detail, we may want to select a closer vantage point of view to the Earth, whereas the geostationary satellite has to be at a height of 36,000 kilometers, we can do a polar orbit, which is sun-synchronous. It means that it crosses the equator every day at the same time of the day, from a height of only about 600 to 800 kilometers, where we can get much greater detail of the content of the Earth's atmosphere. And here is one of the satellites that does that with a hyperspectral resolution. It is called ERS, atmospheric infrared sounder, and you can get measurements of the CO2, nitrogen oxide, ozone, sulfide oxide, methane, among other things. So here is one very interesting outcome. This is a map of the amount of the CO2 in the atmosphere, but over a very small range, where the deviations from the global average are of plus minus 1% in concentration are magnified here. And we see that the red areas are areas where the CO2 concentration is enriched because of mainly man-made emissions of this greenhouse gas. You can see one band at the northern latitude crossing through North America, Europe, Asia, and the westerly winds in these areas are carrying the enhanced concentration of CO2 across all around the world. This picture is average concentration for 1 month, which happens to be July 2009. You see the same feature, but not as strong in the southern hemisphere, where the southern hemispheric industrial countries are emitting, and you see some nice emission point in South Africa, South America, and to a lesser extent in Australia, but the westerly winds are steering it all around the world. So by that we can see where the emissions occur. We can use other parts of the spectrum, like CMACHI, which is scanning imaging absorption spectrometer for atmospheric cartography, which was on Envisat, is on Envisat, which is no longer active, and by ESA. And this hyperspectral instrument is actually using the solar spectrum, both visible and infrared. And you see on the left of this spectral diagram a whole laboratory of chemical species that we can measure with SCIAMACHI. Not only that, also we can measure properties of clouds and aerosols. So that has been very informative. One very well-known outcome of that is documentation of the ozone hole that still exists now over the Antarctic. We don't hear so much about it because it stopped to be worsening, but there is still a long way for it to go to recover completely. And here you see over the Antarctic, the purple area is area with very small concentrations of ozone. Another interesting outcome of CMRG is the documentation of the nitrogen oxides. Nitrogen oxide occurs when there is combustion with very high temperature that occurs typically in diesel engines, power stations, and actually it is demarking the industrial emissions. And you see that indeed there are high concentration on an annual average over US eastern coast, mostly Europe, Northwest Europe and the Po Valley, and India, but by far more than any other place is China, which is now has become the most highly polluted country, and it is very evident. And, so these kind of measurements are a great way to monitor the emissions, the pollution, and monitoring is the first way to know where the problems are and to get into solutions. The emissions are not only of gases, some of them are of toxic nature and others are of greenhouse gases nature, which induce the climate change. Also aerosols, which are tiny particles floating in the air, are emitted, and they can be measured by a variety of methods. The best, most accurate method to measure the vertical concentration of the aerosols with height is laser LiDAR, which is now active on a CloudSat. This is the Calliope instrument, cloud aerosol LiDAR with orthogonal polarization, and you see the illustration on the upper left, and the map shows the annual average concentration of aerosols or atmospheric turbidity, or how much the visibility is impaired by the aerosols, as measured by the Calliope, by that laser radar. And you can see that again, China is highly polluted. We just heard recently in the news that there have been catastrophic concentrations of air pollution, more than 1,000 milligram per cubic meters in northeast China, which are choking the people there. And it shows here even on an annual average basis. These particles have not only climate health hazard issue, but are affecting the climate to a large degree. Each such pollution particle is potentially, when incorporated in air parcel that produces a cloud, it can potentially be the nucleus for nucleation of a cloud drop in the cooling rising air, the very same way as dew is forming on a cold object on the ground when they become cold at night. So if you have a pristine air with over the ocean with very few aerosol particles, as seen in that layer cloud that is illustrated on the left part of the image, then the same amount of cloud water that must be condensed when the air rises is distributed on a small number of large drops. And when the drops are large, they fall fast and they are easy to collide with each other and to produce rain. And when the clouds lose the water to rain, the clouds break up. And the clouds are highly variable over the Earth, and because they are so bright, and they reflect much of the solar radiation back to space, and they are actually serving as the thermostat of the Earth system. And if there are less clouds, we have warmer climate. If we increase the amount of clouds, the globe will cool. So if we have pollution into those pristine clouds, as illustrated by the smokestack from the ship in this image, then the clouds will be formed by a larger number of much smaller droplets, which have, for the same amount of cloud water, much larger surface area, and much more solar radiation would be reflected back to space. This impact of man-made air pollution on the clouds is actually counteracting to a certain extent the global warming due to the greenhouse gases emissions. And however, this effect is highly uncertain and contributes the largest term of uncertainty to our ability to quantify the impact of mankind on global climate and warming. And therefore, measuring the aerosols, the cloud properties, and the precipitation from space is of utmost interest and importance for understanding the Earth system and climate. And I'll show you now an image of such layer clouds over the ocean. On the left hand side of that image, we see the cloud deck as seen by visible light. This is what you would see over the ocean if you looked at it from space. We are looking at area of about 500 kilometers across. But on the right panel, we see a false color image of the size of the drops of these clouds. The more blue colors mean smaller drops. We are able to see the drop size because larger drops absorb more strongly in the solar infrared than small drops. So the clouds actually have color. It would be colored if you could see them in the solar infrared light. And that is one possible way that their color would look like. So you see here the bands, the blue bands, which are actually the polluted clouds due to the smoke from ships. At the edge of the tip of each such area, there is a ship that emits smoke that causes the cloud drops to be smaller. And when the cloud drops become smaller, the clouds become a bit brighter. And those red lines are guiding the eye to there, but they are brighter only very marginally. But in my view, the more important impact is by the clouds becoming composed of smaller drops. The smaller drops are more slowly combining into precipitation. So the air pollution is actually suppressing the precipitation and the breakup of the clouds due to losing the water to precipitation. You see here the color scale of what we call the effective radius of the cloud drops, and when the cloud drops size exceeds about 15 micron, these are the units, then they start to precipitate heavily, lose the cloud water, and break up. So you can see here that when the background of the polluted clouds is smaller than this threshold of 15 micron, the clouds don't change, but when because of the pollution tracks. But when the background is very pristine, the polluted tracks actually are manifested in full cloud cover. And the numbers here are showing the amount of radiative cooling in watts per square meter for the clouds. So actually, in some limited areas, we can cool the Earth or preventing its warming by very high rate of over 100 watts per square meter, and that's a huge number. The uncertainty in that, how much is it occurring, is a major question. How much can we cool the Earth? There are ideas of doing that intentionally over large spaces of the ocean for keeping the Earth from warming, but that is comparable for a patient who takes pills against fever instead of taking the real medicine. And therefore, we need to really, this is not what we really should be doing. So here is an illustration of clouds that are polluted, made out of small drops and do not precipitate, and clouds that are pristine, made out of few large drops and do precipitate. And there is a special mission, a tropical rainfall measuring mission, which is now followed by global precipitation mission, which is the main instrument on board is a precipitation measuring radar, which measures the intensity and type of precipitation inside these clouds. And here is how the tropical rainfall measuring mission see a hurricane over near South Africa in the solar light, but it can actually penetrate inside the clouds and view its structure by the precipitation, intensity of the precipitation radar returns. So you see here the hurricane, you see in the middle of the eye, which is precipitation free and cloud free, and the very intense precipitation around. And the TRIM has also a lightning detector, and we can see on the top panel a map of the lightning, global map of the lightning, and on the bottom panel we see a global map of the precipitation. And you see that there is very little correspondence between the amount of lightning and the amount of precipitation. One would think that where it rains more, there will be more lightning, but it is definitely not so. Most of the precipitation occurs over the tropical ocean, but most of the lightning occurs over the tropical land, and that is because the pollution, aerosols, are suppressing the early formation of rain from the clouds. The water is kept in the clouds, in the rising air, lofting to height where temperature is much lower than the freezing point. And there, instead of gentle liquid rain, it forms ice precipitation, hail, and many ice crystals that when they collide with each other, they charge each other, and that is the mechanism that actually creates the lightning. So here we see how the air pollution is actually contributing to make the precipitation more violent and more intense, with greater lightning. We can. There are evidence also that when there is more air pollution, the intensity of the storms is larger to the extent that not only producing more lightning, but also more hail and even more tornadic storms. And it affects also hurricanes. So we are changing the face of the skyscape of Earth, the very same way that, to the same extent that we are changing the landscape of the Earth, only that we are unable to see it very vividly because we don't know how the Earth, how the skyscape would have seen without our activity. So there is a whole constellation of satellite that is aimed at measuring the environmental properties for understanding all the environmental aspects, but prime that is the elements that are necessary for understanding how much the Earth is going to warm and what is the impact of mankind. One striking example is measuring the sea ice over the Arctic. As we all know, there is a severe trend of decreasing of the cover of the sea ice over the Arctic Ocean. And here we see satellite measurements of the thickness of the sea ice, where the red color shows a thick ice of 5 meters plus. We have radar measurements of the evolution of the sea ice for the last 30 years, and we'll see now time lapse of images. Each image is 1 week through that time period, and we see how the 30 years ago, the ice was very expensive. The time scale is shown in the bottom left panel, and you see that the ice is thinning and flowing out of the Arctic Ocean, and nearly almost vanishing. You see the annual cycles. Here we switch back to the initial stage where the ice was high. Here we saw just a taste of few examples of the vast array of measurements that we can do in the Earth's environment, that we need to take to go out to space above the Earth's atmosphere to sense the atmosphere more accurately. And that requires development of a vast array of technology, which I did not focus so much on the technology, but first, what is it good for, and what it buys to us to motivate us, the young people around here, to go into these directions. So what will come next, that is my view, that major gaps in climate monitoring still require to be closed, especially in aerosol cloud interactions impacts on Earth's energy budget. Although we have so many satellites monitoring, there are still technological challenges that are not yet overcome to monitor what we really need to measure. While we need to develop more advanced satellites, it is still a challenge to maintain the continuity of the climate records with the present satellites in these difficult economical times. The next generation of operational satellites will deliver the kind of data that research satellites are presently delivering. Operational satellites are satellites that are maintained for monitoring the weather, whereas research satellites are testing new technologies and research ideas. So we are gradually moving the research cutting-edge idea to become operational for accumulating the long-term record of these parameters. And I believe that the future will probably bring higher spectral and spatial resolutions to the satellites, so that hyperspectral and imaging probes will converge. I will be glad to answer questions. Thank you.
Highly topical presentation. As we have heard, Cristina Figueres, just a couple of days ago, the head of the UN Framework Convention on Climate Change, has stated that lack of global warming agreement is condemning future generations before they are even born. So I believe that your type of research that's facilitated by satellite technology is crucial. That being said, I think we have time for one or two questions from each site. Do we have any questions from your audience with regards to your presentation?
Hi, good day to you all. My question is, because we live in Israel and we have a deficit of water, how can you use satellite and weather satellites to forecast or to predict the amount of rain and water our area is suffering from us and the world in general?
As you have seen earlier in the presentation, we are able to measure the amount of water vapor, which are the precursor for the clouds that produce precipitation. We measure also the clouds and the atmospheric motions. All that is fed into global weather models that are actually using these measurements as the initiation conditions for calculating the weather prediction. And the weather prediction has improved tremendously because of this satellite input from a prediction limit of about 3 days. Before the satellite era, we're now, due to the improvement in the satellite and computer capabilities, we are able to predict with the same accuracy to about a week. And that includes, of course, quantitative precipitation predictions. That unfortunately it doesn't help us too much for predictions that are at ranges of several months and beyond. More questions?
No further questions. Thank you.
No further questions. Thank you very much. In this case, I would like to pass the floor to Politecnico di Milano in Italy. Do you have any questions for Professor Rosenfeld?
Okay, it looks like Italy has no questions.
Thank you very much. Let's move on to Technical University of München. Do your students have any questions for Professor Rosenfeld?
Yeah, hello. One question, you mentioned the connection between the pollution and the, let's say, harder rains in the, I think it was the tropical areas. How strong is this connection between harder precipitation and pollution?
We see there are climatological studies, for example, over the Amazon. As you know, over the Amazon there are episodes of strong pollution due to burning of the forest. The observations show clearly that during these periods the nature of the precipitation is changing significantly, such that there is more cloud electrification, more lightning, and the same amount of precipitation is redistributed to strong, more intense rain over shorter areas and times. And that is supported also by numerical simulations.
Okay, thank you. But actually, just an add-on question. How strong is it? So if you could say you have twice as much pollution, have you double as strong rain, or is this, let's say, a bad question?
Yeah, I understand the question. It doesn't work, it's not a linear effect. A little pollution have a strong effect on pristine clouds, but when you pollute more and more, then the effect is saturated. And beyond a certain effect, actually, a certain amount of pollution, actually, the air is so much polluted that solar radiation cannot penetrate to the earth, as happens, for example, now in China, and cannot warm or give the energy that is necessary to propel the growth of the clouds and the storm in the first place. So it is similar to other parts of the climate system. It is not a linear but highly non-linear process, which is very difficult to track down and separate from the other components of the system, because we cannot do control experiments in the climate system, and this is our big challenge. That's why we need the measurements.
Thank you. Any further questions from Technical University of Munich?
No further questions. Thank you.
Thank you very much. Then this concludes our morning session. I want to thank once again Professor Amalia Ercoli Finzi, Gian Antonio Magnani, Eduardo Re, Professor Aline Albuchefer, and Professor Daniel Rosenfeld for their enlightening lectures. Your presentations were fascinating, and your dedication to academic advancement of the students who participated in today's lectures is greatly appreciated. I would also like to take this opportunity to thank the technical staff at all sites for supporting and facilitating these lectures, and the European Space Agencies and partners. Hope you've all enjoyed this morning. I would like to remind you also to refer to your local moderators. I would like you to refer to your local moderators to find out exactly what time your local program is starting at, and we look forward to another exciting second part of the event this afternoon. Thank you and goodbye.
קהל נכבד, אתם תחכו רגע שפמליית ה-VIP תצא החוצה. אנחנו רוצים לעדכן אתכם שבשעה 3:10 אנחנו נקרין סרטים על תחנת החלל, ומיד אחר כך תהיה כאן הרצאה בעברית. אלברט כוכב נולד. אנחנו מבקשים שתחזרו לאולם עוד כשעה מעכשיו בשעה 3:10. תודה רבה.